Fine. So this is lecture 2. So in the last class, we were talking about a refresher of the convolution integral and then how the transfer function kind of comes about. But let me ask you this question. So given any system, I'm not putting any constraint on the system. Let's say it's nonlinear, it's time variant, everything, right? So if that is the case, I can do this experiment always, right? Theoretically, I can put an impulse and I observe, I'll get some output, right? So I get some output, let's say I get some output like this, and I do the Fourier transform of this output, right? So I'm going to get some complex expression in frequency domain. And then I say that I'm going to use it for my frequency analysis, right? So then I say that I'm going to use this, the whatever h of j omega I get by, I do the Fourier transform of this. Right? So I'll get some h of j omega. It's a mathematical operator. I have a waveform. I did some mathematical operation. I'm going to get something. Right? So and I do this. Also, I'm going to get something. So is it correct? Incorrect? Any comments? Is the question clear? Question is not clear. Okay. So let's say I took a circuit or network, which is no constraint. It can be nonlinear, it can be time variant, anything. So I apply an impulse to the circuit, and I'm going to get some output. Some waveform will be there. I don't know what it is. Some waveform will be there. And if I say that that is the impulse response of the system, I'll not be inaccurate, right? That's correct. Impulse response is the response to an impulse. So I apply that impulse, I'm going to get an output. So, and with respect to time, let's say the waveform looks like that, right? And then I take a Fourier transform of that waveform. That is also I'm entitled to do, right? It's a time domain waveform. I just put that mathematical operator. I'm going to get some output, and I call this h of j omega, and I say that that is a transfer function of the system. Is that correct or not correct? Why not? Why or why not? Both ways.
The function is the output means like output divided by input, so it will be constant for the system, no?
Yes.
So if the impulse response is same h of j omega we get, that's the transfer function. It will be same for every time. It won't be changing the transfer function.
Okay, so you are saying that I can say that h of j omega is a transfer function of the system, right? Any other comment? Anybody who says things otherwise? Note that I am not put any constraint on the system. This can be linear, non-linear, time variant, everything. No constraint.
Function if it is LTI.
So it's a transfer function if it's an LTI, right? So how many of you don't agree with that statement? Yeah, I got your point. Anybody else? How many of you agree with that statement that it has to be a transfer function? To call it a transfer function, it has to be an LTI system. Okay. So how many of you haven't made up your mind? I mean, now there is no other option, right? All. So either you agree or don't agree or haven't made up your mind, right? So how many of you haven't made up your mind? Okay, so let me, I mean, that's good, which means you're open for persuasion, right? So now the question, let me go back to the previous class, that why was it necessary for something to be called, why was it necessary that I needed the definition of an LTI system? I could have as well done whatever I have done now and analyzed everything. So we spent some time in the first class while motivating why do we need an LTI system.
Everything can be broken into impulses.
Right.
So that is why
Yeah, everything can be broken, but what thing?
every signal is
Right. Good. So every signal can be broken into impulses. That's good. So let's say, so I have any signal, I can break it up into impulses. And the strength of the impulse is basically the weight of the sliver around whatever time instant you are breaking up into. Fine, that's a step. Then
the linear property allows to somehow
right. So one is linear property that will sum. So basically, I can get an impulse for this. I can get a response for that impulse. I can get another response for this impulse. But is there a relation between these two responses? There has to be a relation, right? And that relationship is I can only impose if I know it's an LTI. Right? If I scale it, it should scale. That's linearity. If I shift it, it should shift. That's time invariance. If I am not able to do that, then even though I can write out these integrals and convolution integral, I can always write, it's a mathematical operator, but it won't mean anything. Because ultimately I am interested in figuring out if I give any arbitrary input to the system, what will be my output for that arbitrary input. Otherwise, I'll have to give impulses every time and then find out what is the effective output and then do the calculation every time. So it's not a so boils down to the definition of a theorem, for example. So you do so many, I mean, when you were doing geometry in schools, you had so many theorems, even circuits, there are so many theorems. Why are theorems important? Because I can use that small amount of information that is encompassed in a theorem to prove many other generalized things. Right? So similarly here, if I have to use something, prove something every time, that's not a theorem. That's not useful. Only reason impulse response is useful because the LTI system property is telling us if I scale the input, the output will also scale. That's a linearity property. And if I shift the input, the output will also shift. That's the time invariance property. And since I am able to break up any signal into scaled and shifted impulses, no linearity required for that. It's a property of a signal. I can scale up, I can break up any signal into scaled and shifted impulses, which means if the system is LTI, I should be able to scale and shift this impulse responses also. So this scaling and shifting of impulse responses based on only one information, only one experiment of putting one impulse in and taking the output is only possible if the system is LTI, not possible if it's either time variant or nonlinear. Right? Make sense? Okay, fine. That's an important caveat because later on you are going to see we are going to use non-LTI systems or time invariant systems, and some of these caveats will be very important to understand at that point of time. Okay. So now so wherever we stopped in the last class, we said that this is an LTI system. One property, again, I mean, if I do if I apply an input e power j omega naught t, I get a scaled version of e to the power j omega naught t, and that scaling factor is a complex number, right? And that complex number is basically the response to a complex exponential at the input, right? So I can simply write h of j omega naught to be response to an input e power j omega naught t divided by e power j omega naught t. Very obvious statement, but a very profound statement. Again, you'll see when we deal with systems which are non-LTI. Okay. Now note that h of j omega naught cannot be expressed as a response to the input by response to the output for any signal. Right? If I simply write h of j omega naught, let's say, is equal to output response by input. This is not correct, because I can only express the output as a scaled version of the input only if the input is e power j omega naught t. Right? E power j omega naught t is the eigenfunction of an LTI system in a linear algebra terminology. Okay, so if I have to find out the transfer function experimentally, I'll have to put in a complex exponential e power j omega naught t and then find the output and then scale the output by input. Whatever we get is essentially h of j omega naught or transfer function. Now then we said in the last class that obviously e power j omega naught t you will not be able to apply because it's not a real system, real signal. But I can apply cosine omega naught t, I can apply sine omega naught t. I do 2 experiments, store the data, multiply the second with j and add up. At the output, whatever I get is essentially e power j omega response to e power j omega naught t. Again, this is true only because it's an LTI system, or in this case, a linear system, because I am putting 2 inputs separately and adding them up, superposition, right? Okay, fine. But this is also a clumsy way of finding out clumsy way of finding out h j omega naught t, right? Because you have to do so many steps. So what is the easy way to finding it out? I'm sure all of you know this also. So I know that e power j omega naught t, if the input is e power j omega naught t, output is h j omega naught e power j omega naught t. And in general, h j omega naught is a complex number, which means I have a mod of h and a phase of h. Phase is also a function of omega naught, e power j omega naught t, right? So I can express this as mod of h e power j omega naught t plus phi, which means I can express this as mod of h cosine omega naught t plus phi plus j times mod of h sine omega naught t plus phi. So this is the response to the output when the input is e power j omega naught t, right? So this is the response to the output when the input is e power j omega naught t, or the input is cosine omega naught t plus j sine omega naught t, right? So we are anyway doing an experiment by applying cosine and sine separately. If I only apply cosine now, what do you think the output will be? Okay, maybe the question is not clear. So maybe I repeat the question. So my input is cosine omega naught t plus j sine omega naught t. I know the output, which is h cosine omega naught t plus phi plus j times h sine omega naught t phi plus phi. So input has a real term and an imaginary term or a complex term. Output has a real term and a complex term. Now, can I say that if I only apply the real input, I can correlate that real input to the real output? I can say that, right? So similarly, if I apply only an imaginary part, I can correlate with the imaginary part of the output, right? I can say that simply because your system is real, right? This system, whatever you have, if you apply a real signal to a real system, you cannot get a complex number in time domain. You cannot get a complex number in time domain, right? So that's essentially it, right? So all this analysis is in time domain. Okay. So which means that if I apply, I have an LTI system. Now I apply cosine omega naught t. What can I expect at the output? mod of h cos omega naught t plus phi. Remind you that this mod of h is mod of h of j omega naught, basically, because I have applied a monotone signal. I have applied a signal at only omega naught. Okay. So now there are a couple of important things that you need to be mindful here, or rather observations. Observation one is I'm applying an input of single tone input of omega naught, right? Output is also having a single tone of omega naught. Yes.
H of j omega naught or just only omega naught?
Which part are you talking about? This one?
Yes.
This is h of j omega naught. Okay, I understand why you are asking this question, but maybe go ahead and ask your question.
Sir, because the input is not imaginary and the modulus part, this will be get a function which is imaginary.
But if I take a mod, then I'm only taking the magnitude.
But why we are getting the function which comes under the imaginary input? Which input is imaginary? Like,
I'm not sure if I understand the question correctly. Are you saying that you are okay if I write it as h of omega naught? Mod of h of omega naught?
why we not like this?
Why do we not? Okay, good question. His question is, why are we always writing everything as h of j omega naught? And why not omega naught? Right? Actually, very good question. From a circuit standpoint, I can give you an intuitive answer because it's a circuit course. So what is the, from where do we get these omega naught terms? What in any circuit, from what is the genesis of this omega naught term or omega? That's signal way of talking about it. But in a circuit, frequency operation, can you be a bit more specific? You are going in the right direction. Right. We basically, it's because the capacitance and the inductances have an impedance which are always of the form of j omega something, j omega L 1 over j omega C. So omega never appears in isolation, right? You will always be of the form of j omega. You can have omega squared, which is real because you might end up multiplying something has a s squared term because you have a j omega times j omega, and then you can s squared, but it's still a function of j omega. Right. So from a circuit standpoint, it is probably easier to appreciate why everything is of the form of j omega. But having said that, mathematically, there is no difference. I mean, j omega is also a function of omega. I can write things in terms of omega, but that doesn't convey the full picture. Right. So that's why we write it in the form of j omega. Right. But good question. Yes.
From the earlier part, when you defined h of j omega naught to not be simply output response by input response, like I was considering a simple RC circuit, a low pass filter, and you apply step response at B. So like you'll get some transfer function, right? Which would be the function of S and j omega naught.
Okay, your question is, let's say I have a simple RC circuit. I apply a step at the input. I'm going to get some output. But is that output a transfer function of can I scale the input by the transfer function to get that output?
It would be like 1 by 1 plus SRC, like times the.
Yeah, but what is that S? And what is that omega if the input is a step? Right. So it's a combination of multiple omegas. Again, you have to break up an input signal into inverse Fourier transform and all those things, right? So we are still talking about applying a monotone signal. Input is sinusoid. Okay. Again, a good question. Some of you, might have already figured it out, or some of you might also, this question can come to your mind later on. So if I apply, let's say, any arbitrary input, right? So his question stemmed from, why did I write this inequality? Right? Because if, let's say, you're, instead of applying e power j omega naught, if I applied a step, output, I would have gotten something, right? I don't know, maybe something, if say, right? So if I simply divide this output by input, I'm still going to get a number, or a time domain waveform. But does that time domain waveform mean anything? It doesn't really mean anything. It might mean that it's a response to a impulse, a response to a step, but I cannot really break up signals into steps. right? I have to break it up into impulses and then go back to do a step. That doesn't help too much. So that's why we don't do that. But when coming back to the point of, it is incorrect to say that this is an impulse response because the input is not impulse. It is incorrect to say that it is a transfer function because the input is not e power j omega naught t. It's neither of those, right? Okay. Okay. So I hope this argument is clear why we do not want to write everything as omega naught, h of omega naught. But at times you will see that writing j omega naught becomes clumsy. We just drop everything and just write h, assuming that we understand there is a j omega naught in the argument, right? Okay, fine. So now, the important takeaways from this expression. First important takeaway, and very important takeaway, is the fact that if the input has a frequency of omega naught, output will always have a frequency omega naught, right? It cannot have a different frequency. So directly from this, you can conclude that an LTI system does not change frequency of the input. Right? If an output, if I see and if I know that something is LTI and I observe only the output, let's say having a frequency of 1 gigahertz, right? And then I can for sure say that the input also has a frequency of at least 1 gigahertz. Because if the input doesn't have 1 gigahertz, the output cannot have 1 gigahertz. There is no other frequency component that can translate and come to 1 gigahertz. Right? But I cannot say that only 1 gigahertz component was there at the input. Let me rephrase. So let's say I say that I did an experiment. I don't know what is connected to the input. This is I don't know. And I observe the output. And at the output, I see an waveform which is 1 volt sine 2 pi times 1 gigahertz t. Okay. From here, I see that the frequency is of 1 gigahertz at the output. I can for sure say that the input must have a tone at 1 gigahertz, right? There is a one-to-one correspondence with respect to the frequency of the input and the output. But can I say that the input didn't have a tone at 2 gigahertz? Why not?
There may be filter.
Right. So it can be a filter, right? In frequency domain, where maybe you have a zero, absolute zero, a null at 2 gigahertz, and that might not allow the output to come in at 2 gigahertz, right? But I can absolutely certainly say that if I observe something at the output, I mean, it's an LTI system, the input must also have that same frequency. Now note that if it's not an LTI system, I cannot even absolutely for certain say that, right? Because, I mean, it is possible that, I mean, I have not proved this, but it is possible that this translation of input tone, or that this input to output tone frequency not changing might not necessarily be true for a non-LTI system, which means if I observe some tone at the output and I don't know whether the system is LTI or not, then I cannot for sure say that the input also had a tone at that frequency, right? Again, this is something that you'll encounter later on in the course. Okay. Okay. Any questions so far? Okay. So the first point was LTI systems don't change frequency from input to output. What is the second point? The second point is, if I apply a monotone signal at the input, by looking at the transfer function itself, I should be able to say that the amplitude of the output will scale by how much, right? Because the magnitude of the transfer function is essentially that scaling factor, right? So output scales. So by mod of j omega naught if input is cosine omega naught t or output amplitude, I should say. Output amplitude scales by mod of j omega naught if input is cosine omega naught t or sine omega naught t. Right? That is the second thing I can say. And the third thing that I can say is if there is a phase shift at the output, or even without that caveat of phase shift, if there is a phase shift, I can say that the output has a phase shift of phi of j omega naught, or in this case, by the way, okay, I will comment on this in shortly. Output has a phase shift of phi of omega naught with respect to the input, right? So just to complete the thought of the question that he had raised, we don't write phi of j omega naught. We only write phi of omega naught. Any comment why? Because it is? Yeah, right? It's an angle, right? So there is no point in saying that I have a complex angle, right? So so when you break up your transfer function into h of j of h and e power something, that the argument of the complex e power, the argument of e power term already has j times something. That times something is real. So that is a function of omega naught. That's not a function of j omega naught. So we drop the j while describing the angle. Okay, fine. So again, things that we already know, but sometimes slips our mind when we do come to analysis or design. So let's do let me ask you, given that we know all these three things, let's say I have a LTI system which has a transfer function something like this. So this is mod of h, and let's say the angle or the phi is something like this. And I'm interested at, this is omega, and let's say I am interested at 1 megaradian per second, right? I'm interested at 1 megaradian per second because I have applied an input. So this is my LTI system. I've applied an input at, let's say this is cosine 1 megaradian per second times t. Right? So tell me what will be the time domain output and how should I go about thinking about it? I have obviously haven't given you all the numbers and everything. You can ask for it. So I have a transfer function that I have gotten a priori by putting in an impulse, doing Fourier transform and everything. And after I did a Fourier transform, I broke that Fourier transform up into the magnitude and the angle, and I got these two plots, right? Now that I have motivated you sufficiently why LTI system and everything is important, I go ahead and apply a cosinusoid of 1 megaradian per second. I want to know, without doing any more analysis, what will be the output looking like. So what should I do? Right, exactly. So basically, on this omega axis, I am going to mark out this 0.1 megaradian per second. I'm going to find out what is this point, which is this is mod of h of at 1 megaradian per second. And I'm going to find out this angle, which is also the angle at 1 megaradian per second. And I'll simply say that the output is mod of h j of 1 megaradian per second times cosine of omega naught remains omega naught, so which is 1 megaradian times t plus phi, this is if I call this phi of 1 megaradian per second. This will be whatever the phi. Right? No, the value of phi can be minus, but yeah, but as long as I'm calling it phi, it's plus, right? Okay, so that's essentially the power of your transfer function, that once you have it, you know for any cosinusoid or any sinusoid, you are going to what output you are going to get. Okay, fine. So this is simple. Now, sometimes we like to express all these things in frequency domain also. By the way, this is all time domain. Input is the time domain, output is time domain. I'm trying to relate transfer function to time domain. That's what I did. Now, if I want to do everything in frequency domain, then which means that I have to then take the Fourier transform of the input and the Fourier transform of the output and relate those two, right? So let's do that. If I have h of j omega naught, input is e power j omega naught t, output is h of j. So if I do a Fourier transform of the input, what will I get? What is the Fourier transform of e power j omega naught t? Yeah, I mean, depends upon how do you define Fourier transform, right? Whether the 2 pi will come or not. So as it turns out when you are doing circuits and in some signals processing also, we do not use that 2 pi 1 over 2 pi or 2 pi terms while doing Fourier transform. Inverse Fourier we do, right? So essentially this becomes delta only omega minus omega naught. And the output will be? Okay, let's do the frequency part first. So what will be the, okay, so let me write it this way. So if I plot this with respect to omega, input will be looking like what? An impulse at omega naught. So this is omega naught. This is the impulse at omega naught. What will be the output looking like? This is the input. This is the output. And let's say mod of output. Scaled version of that impulse, and the scaled version, if I'm only interested in the mod, it will be scaled by h of j omega naught, right? So this output will be, so let's say it's scaled can be smaller also. So this is h of j. Right? So that's why, I mean, if I do the Fourier transform of this, I should get h of j omega naught delta omega minus omega naught, right? So now, again, very obvious statement. In time domain, if I break down the signal, the smallest sliver is an impulse in time domain. In frequency domain, if I break down any signal in frequency domain, the smallest sliver is again an impulse in the frequency domain, right? So, but they are related like inverse Fourier and Fourier. So impulse in the frequency domain naturally becomes a sinusoid in the time domain or a cosinusoid in the time domain or a combination of that. And similarly, I mean, if you do inverse Fourier, a impulse in time domain should also have a what? What is the Fourier transform of that? It has all frequency components, right? Okay, fine. So now, let's try to figure out, in most signal processing applications, you are never going to send one single sinusoid, because in principle, a sinusoid does not have any information, because information is basically the level of uncertainty that you can have. If you know a priori what is the amplitude and what is the phase of a signal, then I don't need to get that signal from anywhere. I know a priori. The information will be there. If I know the amplitude maybe varies or maybe the phase varies, I'm interested in the variation of that amplitude and the phase. That's essentially the signal, right? So even though we do all our analysis, assuming what is the response to a single pure sinusoid, that is useless because that doesn't have any information. So ultimately, we plan to send out information, which means that there will be change in amplitude, there will be change in phase. And if I have a change in amplitude and I have a change in phase, it will not be a sinusoidal signal. It will have a spread of frequencies. It might be an aperiodic signal, for example, right? If I have an aperiodic signal, your Fourier transform will not look like a tone, but it will look like a spread. Sorry, this is not T, this is omega. So this is, you need not also be like this, something like this, right? So let's say this is mod of VI G omega. In general, your signal can have a spectrum like this, and the spectrum can also go all the way to infinity. There is no restriction to that with respect to signal processing, right? So the key thing to note is that your signal in the frequency domain need not be tone. It need not also be limited to any set of frequencies, right? It can also have a huge amount of spread. Now the question is, if this is a representative signal in the frequency domain, how do I know what will be the output of it, let's say in frequency domain? So just like we did in time domain, we like to do the same thing in frequency domain. That is, we break up this signal in frequency domain into small slivers, and I find out the response of those small slivers and add them up, right? So what is the response? So how do I break it up into small slivers? So again, let's say at some omega, I say that this is a delta, right? A tone at some omega naught, right? If I know the response to that omega naught, I write that response down. So this response is h of j omega naught e power j omega naught t, correct? Similarly, if I move that tone slightly at a different frequency, I know that, sorry, I made a mistake here. So it should be plus phi. If I move it to a different frequency, let's say omega 1, the output will be mod of j omega 1 e power j omega naught t plus phi of omega naught. Omega 1, sorry. Thank you. Omega 1 t plus phi of omega 1. Right? And so on. And I add them up. Right? And if I do this continuously for small slivers, I essentially get the response to the final output, right? So that is with respect to the time domain. But in frequency domain, if I'm only interested in the output at the frequency domain, right? So what am I saying? If I'm only interested in the output at the frequency domain, let's say I'm interested in mod of V naught j omega naught. So I know that if the input is a impulse at omega naught, output will be a scale version of the impulse. If the input is at omega 1, the output will be maybe a scale version of that, and so on and so forth, right? So I essentially get a series of very closely placed impulses, each of them scaled by the corresponding transfer function value of that particular frequency, right? So now if I know that if the input is like this, output is something like this, then I basically know that if the input is this continuous, if the input is this continuous stuff, then the output will also be this continuous stuff just by scaled by the corresponding value of j omega naught, right? So your output will if the input is now this, the output will be something like this, which means this is scaled by mod of j omega times the input Vi j omega. I'm writing it omega now because now it is a function of omega. I'm not only bothered about one particular frequency point on the omega axis, but for all omega, right? So that is why when you do when you say that your input has the Fourier transform of the input is Vi j omega, the Fourier transform of the output is h of j omega times Vi j omega. Okay. Again, things that we know already from our UG level stuff, right? Fine. Any questions so far? Okay. So then let's take this one step forward. So let's say I have an LTI system. So far we have been applying a sinusoid or an impulse or a generic VI, but let me make it a slightly more specific. And I say that I applied a square wave. And this is h of j omega. I want to find out the output, both in time domain and in frequency domain. Right? So what is the steps? What should I do now? Input is a periodic square wave. Right. So basically, what do I know? What are the tools that I have for analysis purposes? We know that, yeah, Fourier series. No, what I meant was, what have we learned so far or refreshed so far? I know that if the input is an impulse in time domain, I know what the output is. I know if the input is a impulse in frequency domain, I know what the output is. I know if it's a spectrum of input, a spectrum of frequencies are the input, I know what the output is. I know all three. So I have to break it up into one of the three things that I know. Right? So what is the easiest thing to know if the input is a periodic signal? Is the frequency, right? Because I know that from Fourier series, I know that if the input is periodic, I can break it up into series of impulses in what? In frequency domain. Correct? So I know that this I can break it up into, if this is xt, I should not use xt, I should use VIT, because this is not a signal processing course. So this is input is VIT and this is periodic. Then I know that from our, again, I'm not proving this, but I presume all of you are used to handling Fourier series. So I know that this is equal to some summation of some Cn e power j n omega st, where n goes from minus infinity to infinity, and omega s is 2 pi over Ts, where Ts is the periodicity of the signal. Right? Comfortable with this terminology? Okay, fine. And what is Cn? This is 1 over Ts. So not minus infinity, I'm sorry. This is VIT e power minus j n omega st. Yeah, and goes from any t to t plus Ts. Right? It's a periodic signal, which means that I can take any period. I will not lose any information. Right? I can start from any t and take till Ts. Correct? So generally what is done from 0 to Ts or minus Ts by 2 to plus Ts by 2, but it's not necessary. You can start from any t and go to another Ts, depending upon which one is easier to compute in most cases, right? Okay, so we can do this, right? So we do this. Now the question is, so what? The answer to that is, if their input, so what is this telling us in terms of this is effectively telling us that I have applied multiple complex exponentials at the same time. Correct? So I can basically say that if I have to draw a circuit representation of this, I can say that I have so this is my network. I have an input. Maybe this input strength is C0, N equal to 0 means e power j n that goes to 0, that goes to 1. And then I have, so basically this is a DC signal then. And I have another signal, which is C1 e power j omega st and dot, 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 dot. I have another one, Cn e power j n omega st. And I have infinite of these voltage sources in series, both with C negative and C positive and everything, right? And these are simultaneously applied to your input, right? So this is basically, this means this, correct? So I know that now I know that this is LTI, correct? So I know this is LTI, so which means that if I know the response to each of the individual inputs, I can basically add them up and collect them at the output, and that's what my final output will be. So what will be the response to C0 at the output? So it will be H of, what will be in the bracket? 0 times C0, right? That's all, right? Nothing else. Then what will be the response to this guy? H of 1, or yeah, so this will be H of J, no, but what will be the frequency? Look carefully. What is omega naught? There is no omega naught in this here, right? What is the input frequency? Omega S is the input frequency, correct? So here the input frequency is omega S, because I was able to break down my input into periodic signals with the periodicity of omega S, or in time domain TS, in frequency domain omega S. So input is omega S for that particular, for this particular voltage source, which means the output will also be, I have to read out that value from H of j omega at omega S, correct? So this will be omega S. And this will be multiplied by C1, then over j omega st, correct? So if you break up j omega s, if H of j omega s into mod of this and exponent of something, then that exponent will go and add up here and give you a certain phase shift, right? So that is implied. Similarly, you are going to have dot, dot, dot. In general, you are going to have for Cn, you are going to have H of j n omega s, Cn is equal to j n omega st, and so on, correct? So your output will essentially be, I can write this as again summation of Cn Hn, or H of j n omega s for j n omega st, where n goes from minus infinity to plus infinity. Fine? Fine? Questions? Okay. So in frequency domain, what should it look like? In frequency domain, my input should look like what? So again, this is H. So your input should look like, yeah, it's like impulse, one at 0, then something at C1 at omega s, similarly something at minus omega s. If it's a real signal, then the magnitude of these impulses should be symmetric on both sides of the origin, right? So this omega and so on. And at the output, essentially what we are doing, we are saying at the output, this will be, this is input, output. Again, scale version of these impulses. So you're going to have some. So firstly, let me call this one C0, C1, C minus 1. So the output you are going to have, this is C0 times H0. This is C1 times mod of H j omega s, and so on. Right? So very often later on in this course, you are going to see we are applying inputs which have like, which do not have a single tone. They have periodic inputs. They have square waves, all sorts of multiple sine waves, and so on. And you are going to see transfer functions of various types, right? And you should be comfortable in moving between frequency domain and time domain as and when required, based on these very basic principles. Okay, so that's the reason I am trying to give you a refresher of things that will be useful later on in the course. Any questions so far? Okay, so if there are no questions, then let's move on. So more about these things will come. We will look at it at a different perspective later on when we talk about time invariant systems. But let's continue the thought process of time variant system. But let's continue our thought process of time invariant systems as is. But from the standpoint of, let's say you have a simple RC circuit or a LRC circuit or something, right? So which does not have any multiplier or anything like that, right? So I mean, one example that I showed you in the last class, that if you have a multiplier and the multiplication factor is also a function of time, then it's likely that that output will be time variant, I'm sorry, right? But if a system property does not change with time, then it is likely that the system is time invariant, right? So what I mean is, let's say you have built up a system, and at a very rudimentary level, how do I know if a system is time invariant or time variant without running experiment, right? So in a way to think about it is, if you have a system, if you have an RC, let's say a simple RC network, if the response of this RC network, what I get now, what I get 1 second from now, or 2 seconds from now, or 1 year from now, it is always the same for the same set of inputs, then I can say that the system is time invariant, right? It does not change with time. But if, let's say, the component values keep changing with time, right, that I can say is an example of a time variant system, isn't it? So even a simple resistor, let's say you have a simple resistor. Sorry. You have a resistor. I apply a voltage V across it. The current through it is V by R. And let's say I have another control which changes this value of the resistance with time. So that is, resistance is also a function of time. Then clearly this is not a time invariant system, right? Because depending upon when I apply the same input, I can get a different output, right? So a very rudimentary way of thinking about how do you know if a system is time invariant is simply to observe, given a network, are the component values static or they're changing with time, right? Whatever you are calling it as a system, whatever is inside the system should not change with time. If they don't change with time, the system is time invariant. If they change with time, the system is time variant, right? So that's a very, very top level way of thinking about. Yes.
Output looks like incomplete.
In which case?
Yeah, sir. Only with raw magnitude plot.
Correct. Yeah, you are correct. His point is that I have only showed you the magnitude. The phase will also be there, right? So similarly, for each of these, I mean, I have not shown the phase here. So if you have to do that, so what you have to do is, let's say I take this one, I break it up into magnitude and phase. So this will be mod of H. Yes, Cn e power j n omega st plus phi n. Right? So you are going to get another phase plot, right? So based on that phase, you pick up the value of the phase from each point and then add it up. But yeah, good point. Yes.
This square wave example,
Mm-hmm.
you said that it's better to make it into frequency domain, because in frequency there is we have pulses at each omega naught and different omega naughts. But could we have broken it into the number of step responses?
Yes, we could have. Good point. Anvay's point is, so I can as well do this, right? So because your input is, so let me say that this goes on forever. I say that if I know the response to this step, then it seems like the response to this only this sliver will be this step minus this step, right? Yes, you can do this. There is no one stopping us from doing that. You are going to get exactly the same answer, right? I mean, but sometimes the question boils down to which one is more useful for a more general perspective. And as it turns out, splitting everything into the smallest possible sliver or component or whatever in each domain is helpful. So that's why we do that, right? But yeah, there is, I mean, in principle, there is nothing wrong with this. So, I mean, to complete the thought, if you have to do this, so essentially you get, in fact, later on you are going to see that in certain systems, we actually do this also. So if I have to find out the response to the response to this entire thing by the way he is proposing, what I need to do is then say that this is my unit input of interest, right? If I know that unit input of interest, I am going to shift that unit input and then add everything up, right? So maybe after doing all these things, I found out that unit input of interest being that small black stuff, which is something like this. Then I shift my focus to the next unit input of interest. So this next block stuff will also be something like this, and I add all of them up. An infinite series of addition, perfectly valid, nothing wrong. And sometimes used also. Okay, so much time do I have? For 10 minutes. Fine. So so before start, maybe we do not have enough time to go into the next topic in detail. I'll leave it for the next class, but let me try to motivate why we are trying to do whatever we are going to do next. So given that we are now only interested in time invariant systems, and we are only interested in linear time invariant systems, I would like to understand how to analyze a linear time invariant systems given a circuit is given to you, which I know is time invariant, right? I mean, typical examples are RC circuits, right? Maybe something like this. I don't know. I mean, you can write up anything. And let's say I'm interested in voltage across any one of the capacitors or anywhere, right? So the question is, how do I go about making any sense of the output across any of these elements? Now, the obvious answer to that is, what's so special? I write KVL and KCL, I'll get something. That's what it is, right? So if I have to do experimentally, I put an impulse and see what the output is, do a Fourier transform, that's what my transfer function is. If I have to do it analytically, I do not have the tool to sit and put an impulse, then I'm going to replace each of these elements, component values with their Laplace equivalent, or I mean J omega equivalent,